Hello, welcome back. The title of this lesson is called Functions and the Vertical Line Test Part 1. Probably a better title would be What is a Function? And using the vertical line test to test if a graph is a function or not. So up till this point, we've studied an entire unit on lines. And I told you that the equation of a line and studying lines was actually really important because it was the foundation for more important things. This is one of those things. The concept of a function, which is what we're going to talk about here, forms the basis of essentially modern applications of math. We use functions everywhere, and I do mean everywhere. In every math class you will ever take from now on, physics, chemistry, statistics, any engineering class you will take, even biology, they all use functions. Now the good news is that functions are extremely easy to understand. So I want you to think about in your mind, what does the word function mean to you? Well, if I say that this pen has a function, it means it has a job or a purpose, right? That's the thing that it does, right? All right, this piece of paper, it has a function, right? Its function is for me to write things on it, right? This board, these lights, this camera, they all have functions. A function is a job or kind of like an application. So a function in math is very similar to that. A function in math is a mathematical object that does a job. But in math, really, we say that it does a calculation, essentially. So if you think about a box, and inside the box is some kind of computer or some kind of calculating thing, then the job of the box, or the function that the box has, is to calculate something, essentially. And you know, because we have studied lines, you know, y equals mx plus b, we've already studied lines, so you should have already studied that with me. You know that you can put an input into an equation of a line, the x value, and out comes the output. So all of the lines that we have studied in the past, they're all functions. The line is the simplest function there is. Now we are expanding what you know to a broader class of something more than what we have learned, and it's called a function. So let's write something down here. So just to refresh your memory and kind of put it all on the board here, let's pretend that we have a box, and this box has a function, but the function is a mathematical function in this case, all right? And this box, you can consider it to be a computer or you know, some hamsters calculating, some little gnomes in there calculating something, whatever. But on the input of the box, some numbers come in, and these numbers we call x values. Now the x values can be any numbers we want. It could be positive numbers, negative numbers, decimals, fractions. Later on, we're going to study imaginary numbers and complex numbers. Those can go into a function too. So anything can go into the function. That's the input, right? Now inside of this function is some kind of calculating thing. In the past, we said it was like y equals mx plus b or y equals something, right? And so in the past, we would say, I'll just put it up here. We would say something like, you know, y is equal to 2x plus 1 or whatever. But now we're growing up a little bit, and we don't use the y notation anymore. We call it function notation. We say that f of x is equal to 2x plus 1. Now I'm going to explain what f parentheses x means in a second, but just consider for a minute that it's 2x plus 1. All right, so then what happens is this box takes any value of x you put in there, it sticks it here, multiplies by 2, and then it adds 1 to it, and then the outputs come out, and the outputs are what we call f of x, and of course what we calculated was 2x plus 1, like this. All right, now what does this mean? This means that whatever number I put in is calculated, and it's stuck out the other side. Now you should recognize this as a line, right? Y equals mx plus b, the y-intercept is 1, the slope is 2. We've already studied this, and we put the letter y there to introduce you to what was going on. We have to start somewhere in math. I can't just dump functions on you the very first time you graph something. Everybody would get lost. So what we do is we say, you know, y equals mx plus b, you get used to graphing things, and then after you understand lines, then we expand it and we say, okay, a line is just a class of a bigger thing called a function. And a function is what we use going forward. Now this f parentheses x, this does not mean f times x. You got to erase that from your mind. F parentheses x here, it does not mean f times x. F means function. The parentheses, you say the word of. So you say f of x. I can write this down over here. F of x. So literally the way you read this, f parentheses x, f of x, it just means in words, the function of x is equal to 2x plus 1. Because what does it mean to be a function of something? All right, I'm going to bring an umbrella is a function of if it's raining or not. So the input is if it's raining, I take an umbrella, and if I don't, then I don't take an umbrella. All right, I'm going to brush my hair, right, which hair I have left, is a function of is it morning time or not, right? So when you say something is a function of something else, you know, I'm going to put salt in my soup. That's a function of is there a lack of salt in the soup? So when you say something is a function of something, all you're saying is you're doing something, or calculating something in this case, dependent on something else. When we say x is a f of x, it's a function of x, we just mean that the calculation depends on x. X, we actually say, is the independent variable, and f of x is the dependent result that comes out because it depends on x, all right? So when you see f parentheses x, forget about multiplication. It's not multiplication. It's the same thing as the letter y was a placeholder for an output value, but here, this more accurately represents what happens. You can envision these parentheses being the box. X goes into the box, f is the function that we're calculating on the inside, which is this thing, and then the output of the thing is whatever the output of the calculation is. So let's take a quick example. If I say x is equal to 0, then f of x, but in this case x is 0, is equal to f of 0. And what happens when I put 0 into my calculation? This is what the function is, 2x plus 1. 0 goes here, make 0, and you get 1 as an output. So we say f of x, which is f evaluated at x equals 0, is equal to an output of 1. This is the same thing as y equals 1 in our previous way of thinking about it. What if I say x is equal to 1? Then f of x means it's a function of x, but in this case, x is equal to 1. So this is not f times 1. This just means the function evaluated at x is equal to 1. 2 times 1 is 2, plus 1 is 3. And you see the idea. I can do, negative 4 here. X is equal to negative 4. F of x is the function evaluated at x is equal to negative 4. It's dependent on this input value. And then 2 times negative 4 is negative 8, but negative 8 plus 1 is negative 7, and there's my output. So it's literally inputs, outputs, inputs, outputs. The same thing we did when we graphed lines, all right? But there's one important thing I need to bring to your attention that we're going to get to here as we graph these things. And that is, for it to be called a function, there needs to be what we call a one-to-one relationship between the inputs and the outputs. All it means is that for every input you have, there's only one output, one and only one output. They form a unique pair. Here, when the input was x is 0, the output f of x was equal to 1. When the input was 1, the output f of x was 3. When the input was negative 4, the output f of x was equal to negative 7. There is a pairing here which we can graph x comma f of x, or x comma y if you want to think of it like that. And then 1 comma 3 and then 0 comma 1, they form a pair. But it's one-to-one. For each input, there's only one output. I want to say that again. For each input to the function, there's only one output. When there's one-to-one correspondence like that, one input, one output, we call it a function. There are some situations when that's not true and we call it something different, and we're going to talk about that right now. But before we move on, let's consider a different example, because one example, not so great to learn from. So let's consider really quickly another example of another very simple function. All right, so the input to this guy, as always, is x. But on the inside, let's say that f of x, which just means the function evaluated at x, f of x, is equal to x squared. So you see, this is not a line. This is something different, right? Then the output is going to be, just like what we said, f of x is equal to x squared. So numbers come in, we calculate, and then numbers go out. But these numbers, this is not a line. And up till now, we've only studied lines. But you see, functions can have infinite variety. It's like a garden or a flower bed. There's tons of variety of functions, right? Lines are prevalent lots of places, but there are other situations when this pops up in nature. So let's take a look at this. What if x is equal to 0? Then f of x means this function evaluated at x is equal to 0. Well, if I put 0 in here, 0 times 0, that's what 0 squared is, the output is 0. What if I put x is equal to 1 here? Then f evaluated at 1, f of x, f of 1, is equal to 1 squared, which is just 1. What if I put a negative number in here, negative 3? Then f evaluated at negative 3 means negative 3 times negative 3, because x is negative 3. And that's going to actually be a positive 9. So 1 input, 1 output. 1 input, 1 output. 1 input, 1 output. So because a function has to have for a single input only 1 output, then we know that this thing here, this function, listen, we know it's not a line, is actually a function as well. And this one is a line, which is a function as well. And by the way, I will tell you, when you have something squared like this, you might say, why have I been studying this stuff? Well, just one example, the law of gravitation, I'm not going to write it down, has a square in there. It has a function with something squared. The law of attraction of electrical, like electrons, how they repel each other, or a proton and an electron attract. It has a square in there. When you throw a baseball, the curved path that it makes through the air, that curved shape, when you write down the equation for it, has a square in there. When you drop objects and they land on the ground, how long does it take? There's a square in there. So these things pop up all the time, and we learn about them going forward. So now that you have an idea about what a function is, kind of like from a calculation point of view, I want to talk about how to figure out if a certain graph is a function also, and we have something called the vertical line test. So here we have a graph. We have x-axis, which means this direction, y-axis means this direction. Then we have a graph here. The input is the x values, and the output here, normally we put y up here, but when we're growing up a little bit, we start to put the xy graph to the side, and we call it f of x. So instead of graphing x comma y, you're graphing the input x comma f of x. But keep in mind that it's exactly the same thing you already know. You put numbers in the past, we got y values out, we make x comma y, and we plot it. This is the same thing. It's just we rename the y output, we call it f of x now. And I know it's a little bit of a pain, but that's just the way it is. We have to put the y values on the side and start to talk about functions. So anytime you see f of x, you can think of it as the y value. Now, we want to figure out, is this graph a function or not, right? We can see that we put x values in and we get outputs f of x out. So when x is 0, f of x, the output, is also 0. When f is, let's say, 1, 2, 3, the output is 1, 2, negative 3. When the input is 1, 2, 3, 4, 5, the output is 1, 2, 3, 4, negative 5. Let's go the other way. When the input is negative 2 here, the output is positive 2. So you see, this graph represents inputs and outputs. The inputs are along here, and the outputs, f of x, are how far up you go. All right? Now remember, it's a function if for a single input, you only get one output. And the easiest way to check that is just to look at the graph and ask yourself something called the vertical line test. Basically, what you want to do is try to slice this thing with a vertical line. You can put the line anywhere you want. And if it only crosses in one place, then it's a function. And if it crosses in two places, or more places, then it's not a function. So if I draw a line right here, it only slices through the function in one position. If I draw a line over here, again, one position. Here, one position. Here, one position. No matter where I draw a vertical line, it only crosses, I could go down here if I want to, in one position. So because this thing passes the vertical line test, where it only crosses in one spot, we say it is, yes, a function. Now, I want you to think about for a second why this vertical line test actually works, right? The reason it works is because a vertical line test is a way to check that if you only have one input, you're only getting one output. You see? Because if I only cross a vertical line in one position, it means for any one input, I only have one output. For any one input over here, I only have one output. And we're going to see more graphs in a second where actually if it fails the vertical line test, then there's not a one-to-one input-output relationship. So let's go on to problem number 2 and ask ourselves, is this thing a function? So again, the x values are on the x-axis here, and the output, we used to call it y equals whatever, but really we're going to grow up a little bit and we're going to call it f of x. These are the outputs, the functions of x, after we calculate the output. Does this thing pass the vertical line test? Well, if I slice it over here, it only crosses in one place. If I slice it down here, it only crosses in one place. No matter where I go, it only crosses, a vertical line only can slice through this thing in this graph no matter where I go, even though it gets steep. It only crosses in one place no matter where it goes. So it passes the vertical line test, so we say yes, it is a function. Yes, it is a function. All right, so let's get to our next example. We're going to ask ourselves, is this thing a function? Well, remember that the inputs are the x values on the x-axis here, and the outputs are f of x, which are the y values essentially there. And we want to ask ourselves, is this thing a function? So we start to slice this thing and we see, okay, immediately we fail the vertical line test because a vertical line cuts in two or more, in something other than one place. And you can see no matter where you run this thing, it's going to slice twice, except maybe right at the tippy top, maybe it would only be once. But if it only fails in one location, it only takes one portion of the graph to fail the vertical line test, we say it's not a function. So we say not a function. Now you might say, what's this thing called? Well, it has a purpose. It's a sideways one of the things that we looked at before. This thing has a purpose, but it's not a function. And the reason it's not a function, yes, it fails the vertical line test, but I want you to understand what you're doing. The reason it fails and it's not a function is because for this thing, the one-to-one relationship for a single input, you only get one unique output, it fails. Because look right here, look at the green line. If I put an input of 1, 2, 3, 4, what outputs do I have? I have two different outputs, right? Because right here, this coordinate right here is 4, 2. And right here, it's 1, 2, 3, 4 for x and -2 for y. So you see, if I put into this guy an input of x is equal to 4, then I don't get one output. I get two different points, two different outputs. Yes, you can still draw a pretty graph. You can still connect the dots, but it's not a function. And it's not a function because when I give an input, I have more than one output. That is what a function is. A function is a mathematical computation that takes inputs, x, and delivers outputs, f of x, where for a single input of a unique value of x, only one output uniquely comes out for f of x. That is what a function is. And over here, for every input of x we have, there's only one single value of output that you get. So it passes the vertical line test. For every input you give for x, it only gives one unique output for f of x. So it passes the vertical line test, so it is a function. But for here, for every unique independent input of x, I have two outputs here, these two. Right here, I have two outputs, these two, for a different value of x. Here, it fails again everywhere, and that's the reason it's not a function. All right, let's take a look at the next graph here. We have, of course, our input x, and we have our output f of x. And is this a function or not? Well, if I pick a random spot, draw a vertical line, I only have one crossing. I go anywhere else, only one crossing. This means for any given input, I only have one unique output, passes the vertical line test. So yes, this is a function. Okay. Take a look at this one here. This one looks weird. Let's see if it's a function. Does it pass the vertical line test or not? Again, inputs over here, and the output is a function of x. Here I only have one crossing. Here, only one crossing. Here, only one crossing. Only one. Everywhere I slice, I only have one crossing. This means for any x value I have, I only have one unique output. So yes, this is a function. All right. Now finally, take a look at this. This is called an ellipse. So for inputs here, I have, let's take a look at what we have right here. is this thing a function or not? Well, you can see immediately it's not a function because it fails the vertical line test on the first try. I have, for a single input here, this is -3, I have 2 points that are the output. For this point of an input of x, I have 2 points that are an output. The only place really is at the ends of the ellipse where you might have 1 point. Everywhere else fails the vertical line test, so this thing is not a function. All right? Now, you might say, well, only functions are important. Well, really, that's not true. Functions we are going to study a whole lot more right now, but we actually need to understand things that are not functions as well. For instance, this ellipse is not just a pretty shape. It turns out that all of the orbits of the planets around our sun, they're all ellipses. You know, a lot of times students think they're circles, right? But actually they're not. They're all ellipses. Some are stretched more and some look more like circles, but they're all elliptical. So this shape, even though it's not a function, is important. It's not a function. We call it a relation. You can just call it a graph if it's not a function, and you can just call it a relation. It does have a relationship. There are inputs and there are outputs, but because there's not a one-to-one input to output relationship, it's not a function. And so if it fails that vertical line test, that's why it fails. A lot of students know how to do the vertical line test, but they don't know what they're doing. They don't know why it fails and why it's not a function. The one-to-one relationship, one input, one output, that's what it takes to be a function. So practice these yourself. I'd like you to really go through them yourself. Draw your little vertical lines. See if you understand why some of these are functions and some of these are not. Follow me on to the next lesson. We'll continue to build your skills.